we've been calculating the integrals, in essence, to find higher functions. It's a strange way to put it, but we kind of think of it that way. And in business applications, the obvious application to this is if we know the marginal profit, we can find the profit function. And that's what we've been practicing doing. But integrals can also be used in another way. They can also be used to calculate the area under a graph. But believe it or not, this actually has business applications, and we will see that very shortly. Now, here we're going to start working with the definite integrals. Before we've been working with indefinite integrals, and we said that we're looking at the antiderivative over the entire range from negative infinity to positive infinity. Well, now we want to look to a defined area. And if you look at this, the only thing that's really changed is on the integrand sign, we have here a 0 at the bottom and 1 at the top. Well, this is simply meaning that we're going to look at the area under the graph from x is equal to 0 to x is equal to 1. Now, whenever we have the integrand signed and we're doing the definite integral, again, we're not doing the entire integral. We're looking at just the area from x is equal to 0 up to and including x is equal to 1, and hence the numbers here. Now, you notice that the 0 is on the bottom and the 1 is on the top. And whenever we do this, we're just simply putting the smaller number on the bottom and the greater number on the top. So if we were looking for the integral from minus 5 to 12, we would put the minus 5 on the bottom and the 12 on the top. So it doesn't matter if the numbers are negative or positive, we put the smaller on the bottom, larger on the top. Now, if we want to find the area under this function, well, hopefully you realize that the function here is x plus 0.5, and that's going to be a straight line. It's going to, the y, if we did this function just written as y equals mx plus b, well, b is going to be the y-intercept here at 0.5, and it's going to have a slope of 1 from there on. So it's a little hard to see, but this line is actually supposed to be blue. So this is the function, and the yellow is all of the area underneath of the function. And that's what we're saying here. We want to find the area, we want to find the integral from 0 to 1, the area from x is equal to 0 to x is equal to 1 of this function. That's going to be the area under this graph. Now, when we're doing this, what we actually mean is we want to find the area from this function to the x-axis. And we'll see why in just a second. We'll notice here in this particular function, all of the area is above the x-axis, and so when we get answers on this function, of course, they're going to be positive. And the area under here we would call positive area because it's all above the x-axis. Now, to find the area, there's different ways that we can do this. One of the ways with something simple like this would be to say we can break this area here down into this rectangle and this triangle. So the area of this rectangle is going to be the height, which is 0.5 times the width of 1. 0.5 times 1 is going to be, of course, 0.5, 1/2. And the area of a rectangle is 1/2 times the base times the altitude. Well, the base and the altitude are both 1 in this case, so 1/2 times 1 times 1 is 1/2. So the 1/2 area from the rectangle plus the 1/2 area from the triangle equals 1. So now we're getting into something that's a little bit different. When we're doing the integral from 0 to 1, we end up getting an answer that's a number, not a function. So whenever we're working with the definite integrals, our answers will always be numbers, not functions, not formulas. So keep that in mind as we're doing the work. Just putting in the definite integral of this area here changes the problem rather significantly, actually. For this function, it was pretty simple to calculate this area. But there are other functions where it would be a little bit harder to calculate the area. Well, if we wanted to find the area, the definite integral of this function, now here they're starting it from a point here, at A, when x is equal to A, and here x is equal to B, it's going to be over the interval. We're going to find the integral over the interval from A to B, lowercase a and b here. Well, we notice here, this function, this part of the function here, b, the area from the function down to the x-axis, well, this is all going to be, this is above the x-axis. So we would call this positive area. We know that area is always measured positively. And how do you have a negative area? When you're finding the area of a rectangle or any shape. Well, since it's above it, we refer to this as a positive area. Here the area is below. The area is actually a value, but we're going to say that this is negative area because the area is below. We're looking, again, from the function is this blue line. So in here we're looking from the function line up to the x-axis. And since all of this area is below the x-axis, we would simply refer to this as negative area. So A and also C here are negative areas, and B and D would be positive areas. When we're doing the definite integrals, if all of the area would be above or below, we could simply say that it's the sum of the entire function. In this case, because some area is above and below, what we do is we take the area that's above the axis, namely here area, the section here B and D, we add them together, and then we subtract out the negative area. Here, the area that's below the x-axis, and over here at C as well. Since the areas are positive, we end up doing it this way. The area of B and D minus the area of A and C will give us the area, the integral from A to B of this function. So this is the concept of that we are doing. We know that area is not negative, but we can think of it as negative. If we thought of it as negative, we'd say, well, this number is minus, plus, minus, plus. We just add them together. Technically, area is not negative, so we write it this way. But usually, students think of it the other way, that this is minus area, minus area, plus area, and you just add them together to get the total area. The sum of the areas, excuse me, not necessarily the total area. Here's another function that would be hard to find the area of. It's not nice and easy lines. We could try to make rectangles and triangles, and it would just kind of get hard to do. Well, one way to do this is called Riemann sums. And when we're working with this, we can use geometry, but if we can break it down into small rectangles and use just rectangles, it would make it easier. This method is, again, called Riemann sums. In essence, what we're going to do is take the same function here and break the area under it into rectangles. Now here there are, of course, 5 rectangles. We're taking the area from 1 to 3 and breaking it down into 5 evenly spaced points, and then making these into rectangles. So the first one would be here, the second one would be here, third, fourth, and fifth. Now, calculating the area of rectangles is really simple. Of course, it's simply the height times the width. And if we did this, the area that we got with 5 rectangles would be the orange area here. And we notice, well, we're missing this area here. It's not real accurate. We're missing some area here, and up here. Here we have too much area. It includes the section that part here that should not be orange. Say, well, we could probably say this area is about the same as here, so these two kind of even each other out, cancel each other out. But our estimate would still be low using this method. Well, we could get it more accurate if we increased the number of rectangles. Instead of doing 5 evenly spaced rectangles, what if we did 10? That's going to make it more even, or closer, more accurate, I should say. So the first one, well, we're still missing this one. We're still missing this section here on the second one. We're still missing this one. Oh, we have some extra here that helps to offset some of these, but we're missing some, missing some, missing some, missing some. A little bit extra. It's the area, measuring the area under the graph is going to be more accurate, but not 100%. Well, as you imagine, if we wanted to work with this, we could make, instead of 10 rectangles, we could make 20. And if we did 20, then it would look a little something like this. Now 20, this is much more accurate. We realize, well, we're missing some small areas here. There's a little bit extra here. It looks like it doesn't quite make up all of this. We're missing some here, a little extra there. It's closer, but still not quite right. Well, what if we, instead of doing 20, did 40? Well, it's getting, you can still see the orange drawing the lines. The edges are black, and it makes it look like it's half black, but really it's the whole area. If we got a magnifying glass, we'd see, well, there still are some missing areas here. There's extra here, and that helps to offset some of the ones that we're missing. And we would continue to find the same thing over here as well. Well, this would be much closer than any of the ones that we did before it. Well, eventually we could get the rectangles so close together that it would be hard to see the orange because of drawing the black sides. And it would look a little something like this. Well, here we've gone from 40 to 80. And we realize, well, that's going to be much more accurate. It really is looking like it's going to be the area under this particular curve. Well, to be 100% accurate on this, what we'd have to do is draw an infinite number of these. And if we drew an infinite number of these, of course, the sides would make everything look totally black. In essence, there's an infinite number of rectangles here, and we'd say that each the bottom of each of these is infinitely small. There's an infinite number of rectangles here. How wide they are must be that they are infinitely small. So if we wanted to find the area under the graph, we would want to do all of these. Or how would you do the sum of an infinite number of rectangles? Well, what we can do is look at one of these rectangles, say the first one here. The area of this would be the height of this. In essence, it's going to end up being 2 in this case. Well, if we put in an x of 1 in our function, we will get a value of 2 out. That's our y value, which is also our f of x value. And f of 1 would equal 2. So that's going to be the height of it. What's the width going to be? Well, we can refer to this as d of x, or dx. Now that looks familiar. Yes, it should look familiar by now. So the area of the rectangle then is going to be the function f of x times x, dx. Think of it as the derivative of x, or the width of it. So if that's the case, we want to find all of these rectangles from 1 to 3. That's going to be the integral of this. The integral sign actually grew out of the medieval times. During medieval times, they used an elongated s to mean sum. Now we use the Greek letter for sum. So this has stayed with calculus as like an elongated s. It really is meaning the sum of all of the rectangles from x is equal to 1 to x is equal to 3. So it's going to be the area of each rectangle, the area of the rectangle from x is equal to 1 to equal up to and including x is equal to 3. So that's going to be the integral from 1 to 3 of f of x dx. So when we do this, when we calculate the definite integral, we are actually calculating the total area that's under the graph. And since we're doing an infinite number of these, it is accurate. Now, to actually find the value of this, we use the fundamental theorem of calculus. And the fundamental theorem of calculus is this. Now, of course, in math, there's always some things to make sure we're all on the same page, we're understanding the same thing. That our f of x that's here, it's a continuous function from the interval from a to b, including a and b. So the integral from a to b of f of x. F of x is continuous. Well, that just means that there's no gaps in the function, that it exists from a to b, and it's not like if a was 3 and b was 5, it's not like you're missing a point at x is equal to 4, or you're missing a whole range from from 3.5 to 4.5. it exists over the entire range from a to b. And of course, capital F of x is the antiderivative of f of x. So, the fundamental theorem of calculus says that the integral from a to b of f of x dx is going to be the integral of f at b minus the integral of f at a. So, basically that means our x range goes from a to b. We find the antiderivative of f of x, and we do an f of b in it. If we were doing it from 3 to 5, this would be an f of 5. Put 5 in for x in the antiderivative, minus the f of a, which if, again, we said this was from 3 to 5. We do a capital F of 3. Put in 3 for x in the antiderivative. So in application, here's an example problem. If we wanted to evaluate the integral from 0 to 5 of this simple function, 2x minus 4, well, we know that it's going to be an f of 5 minus an f of 10. So we need to find the antiderivative and do an f of 5 in it and subtract an f of 0. Now, when we do this, the integral is again this, and we remember this is using the simple integration formulas. We can break it apart into the integral from 0 to 5 of 2x dx plus the integral from 0 to 5 of minus 4 dx. And when we do that, this is a number, so it can come outside of the integral. And we take the integral of x from 0 to 5, and here the 4 comes out, and we're left with a 1 in here, and we remember that really it's in the form of x to the 0. But as before, we know that the answer to the integral of just this is going to be minus 4x. We can just skip this step, but it's there for clarity's sake. And then we use our formula. The one thing that's new here is here we have this 0 to 5 with this funny bracket here. Well, this replaces the integral sign. When we actually do the simple integration or the u substitution, we lose the integral sign because we're actually calculating the integral, finding what it is. You wouldn't leave that sign there because when you were done, that would mean you'd have to take the integral again. So we replace it with this symbol, which simply means that whatever follows in here, you're going to evaluate from 0 to 5. So it should be feel very similar to this because it is. So 2 times the integral of x, well, we use the simple integration formula for this, minus 4 times, and we do use the simple integration formula here. And of course, when we do all of this together, this is 2, that crosses out with that. We get 2x squared minus 4x. The other way that we see this, I'm simply showing you both ways that are common from what I've seen. This is the second way, and this is the way that the book uses. So I will use it from here on. It's what you'll see on the exam. When we get this together, the integral will equal x squared minus 4x, and this means the same thing as this, that you're evaluating it from 0 to 5, when x is equal to 0 to x is equal to 5. Now, we do that. We do an f of 5 minus an f of 0, like we said we needed to do up here. Well, an f of 5 means we're just simply going to put 5 into this function. So it's going to be 5 squared, which is 25, minus 4 times 5, which is 20. Now we want to subtract f of 0. Subtract f of 0. We put in 0, we get 0 minus 0, which is what I have here. So of course, 20 minus 5 is 5, minus 0 equals 5. So again, this is an area. This is a number. It's not a function or a formula. It's a value. So whenever we do the definite integral, our answer should be a number of some kind. Now, you may ask a question. Why didn't we include the plus c with this? Well, we don't need to. And the easy answer for that is that we don't use it because it cancels out. When we did the integral from 0 to 5 of this function, we got 5 as an answer. And I just copied it here, what we had from before. The antiderivative was x squared minus 4, and we're evaluating it from 0 to 5, and we got 5. Well, let's put in the plus c. So if we put in the plus c to this, it's x squared minus 4x plus c evaluated from 0 to 5. So we do the same thing. And f of 5 becomes 25 minus 20 plus c, minus an f of 0, which is 0 minus 0 plus c. Well, of course, that's going to be 5 plus c minus 0 plus c. And the minus sign, again, gets distributed to both of these. So this becomes 5 plus c minus 0 minus c. Well, obviously, 5 minus 0 is going to be 5. Plus c and minus c, they cancel each other out. So we're left with just the answer. So obviously, we don't really need the c in there. Every time we do this, it's going to cancel itself out. So why bother with it? Why take the extra step, do the extra work? Concept-wise, if we had the function, when we're doing this, if we add on, if we're looking at this function, the x squared minus 4x plus c. If c was 1, that's going to take these values and push them up 1. So let's say that the value would be here. If c, if we do a x of 5 into it, it's going to take the same equation and push it up that 1. Then we're going to subtract f of 0. That's going to be the same, put in f of 0. Then it's going to subtract that 1, take that 1 and move it back down to where it started again. So even on, if we were to graph this, we would realize it's going to move it up and then move it right back down again. If that didn't make sense, don't worry about it. It's applying what we learned before. You can ask in class for a more visual answer to it. But the important thing is to remember that when we do the definite integral, we don't have to worry about the plus c. We'll end up with just a number. Now, in working with business problems, whenever we're doing integrals, we're obviously always going from what we think of as the lower function, the marginal profit, up to the profit function. So all of the homework problems will go around this marginal profit or marginal cost or marginal revenue to find the higher function, cost, revenue, or profit. Now when we're working with definite integrals, we actually are limiting it to a certain area, certain x values. So the application for that, using here marginal profit, would be to find the difference between increases and decreases to a function. When producing x units, your company's marginal profit is this function. Find the extra profit earned from the sale of 3 additional units if you currently produce 5 units per day. Well, if we were going to graph this function, finding the integral of this is going to be finding the area under this function. Well, this is our marginal profit function, and it's the red line here. We're interested in it just from the area from 3, x is equal to 3, to x is, 5, to x is equal to 8. Well, why is that? Well, we're saying our current level of production. We currently produce 5 units per day. Well, that's here. And we want to find the extra profit that's earned from 3 more units that would be sold, that we produce it and sell it. Well, if we have 5 units now, 3 more units is going to be 8 units. So we're interested in this black area here under the graph. This will be our profit function. Now, technically what's happening here is we want to find the increase. Well, currently, the value of our profit at 5 would be this box here, this rectangle here. And that's going to be our profit from just 5, and our profit from 8 is going to be up here, but the increase between the two is going to be this small, almost rectangular shape here, and that's the area that we're trying to find, and that's what the fundamental theorem of calculus makes it easy to do. If we take the antiderivative and do a capital P, a profit function of 5, and subtract the profit function of 8, then we will get that area that we're looking for there. So basically what's happening here is we want to do the integral from a to b of our marginal profit to find our profit function from a to b. Which one is our a and which one is our b? Well, the integral of a, or from a, is going to be 5, as we're starting with where we currently are, and we're going up to a b of 8, because we want to do 3 additional, we're going to sell 3 additional units. So again, a is always the smaller number, b is the larger number. So now that we know what our a and b is, we know what our marginal function is, so we plug that in. We're going to find the integral from 5 to 8 of our marginal profit function, which is 100 plus 50x minus 3x squared dx. Now, we know that we want to eventually do a p of 8 minus a p of 5, but we need to find the antiderivative first. So, we run through our laws. We can use the simple integrating formula here. So we get 100x, the integral of 100 is 100x, plus 50x, 50 times the integral of 1/2 x squared, minus 3 times the integral of x squared, which is 1/3 x cubed. And again, we're evaluating it from 5 to 8. So now we can put all of this together and say that the integral from 5 to 8 of our marginal profit is going to be our profit function, which is 100x plus 25x squared minus x cubed, and we're evaluating it from x is equal to 5 up to x is equal to 8, including 8. So we do an f of 8 minus an f of 5. We simply put 8 into this function and then subtract an f of 5, putting 5 into this function. If we do an f of 8, it's going to be 100 times 8 plus 25 times 8 squared minus 8 cubed, and we're going to subtract an f of 5. So it's 100 times 5 and 25 times, well, 25, 5 squared, and minus 5 cubed. Now, when we do the math, we're going to get 100 plus 1600 minus 512 minus 500 plus 625 minus 125. Now from here, most students simply add this up and add this up to get this kind of thing. So 1880 minus 1000. And of course, when we subtract the one from the other, we get 888 litas. So the extra profit earned from the sale of 3 additional units is going to be 888 litas. Now some students prefer to do this a little bit more the algebraic way, which would be to say, this is going to be 800 plus 1200 minus 512 minus 500. Now remember, once this minus gets distributed to each number inside of here. So this becomes minus 500 minus 625 plus 125. So if you do it that way, don't forget that's what you need to do. Or if you simply add it up, then it becomes a little bit easier to see. Either way is correct. So the applications aren't too difficult. It's actually doing what we've done before, everything that we've done before actually. We find the antiderivative, and then we just simply do an f of whatever this number is on the top minus an f of whatever this number is on the bottom. So it's not too difficult to do. And we actually find that it's more accurate than we learned in chapter 1, I believe it was, a way of estimating it. This way is actually more accurate, more concise. So this is the kind of thing you'll see in the homework. And the homework, we're again back to chapter 6, so it has more business applications, word problems to apply this to. But again, working with the fundamental theorem, we'll get a value for an answer instead of a function or a formula. So when we're working with this, we're going to usually be in business settings, so we're going to end up finding it in litas or euros or dollars or Great British pounds, whatever it may be. And of course, you can also, if you know your rate of production, you can find your production, as well as cost, looking at marginals, cost, profit, and revenue. You can also apply this to production as well. So, again, this is the homework. It's also on Moodle. If you have any questions, We'll see you in class. Have a good day.